Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tare, and this is my continuing feature on the Math Lovers book, a 3-volume series I wrote from 2019 to 2022 that's available on Amazon.com. In case you're interested in buying a copy, you can buy any one or any combination of these 3 volumes. They're each available both in Kindle and paperback. I've already talked about my series in several other videos. You can check those out as well. But anyway, today is my third and final talk about relations. This is in section 5.4 of volume 1. And today I'm going to talk about how to graph relations. So anyway, let's begin. Um, so I'm just going to give you 5 examples today of graphs of different relations. And I think you guys by now, if you've been watching my videos, you should know what a relation is. It's just a set of ordered pairs of points in where the first element is an element of one set, which we usually call capital X, and the second element is an element of another set, which we usually call capital Y. Usually x and y are equal. They don't have to be. In this example, I'm letting x and y both be the set of natural numbers. And now we've got the points. You can think of these as points. 1 comma 1, 1 comma 2, 1 comma 4, 2 comma 3, 3 comma 1, 4 comma 2, and 3 comma 5. And this is just graphing points. I think you guys probably learned how to do this in high school. So we just plot them on what's called a Cartesian graph, the XY plane. So we've got the x-axis going to the right. We've got in this example, since both x and y are both positive, we don't need to go negative. So we're just showing the first quadrant, which would be the x-axis going off to the right, and the the y-axis going up. And now we just plot these 7 points, and you can see where they lie in the xy plane. And before I get off of this, I'm just going to say one more thing about this. This is a relation, but this example is not a function. I'm going to talk about functions in the next few videos. A function is a special type of relation, but it's a relation where you only have at most 1 point on any vertical line when you plot it like this. So anyway, so you can see at a glance it's not a function, but it is a relation. And now let's do another example. How about again, we're going to let our x and y be the set of natural numbers, and now we're going to get our relation be equality. So, in other words, x comma y belongs to this relation I'm calling R2 if and only if x equals y. And I think you can see that if we do that, if we plot these points, 1 comma 1, 2 comma 2, 3 comma 3, so on, you're going to get points on a diagonal line. It's really just a diagonal line. I didn't show the origin in the same place in this graph. Maybe I should have. I don't know. But if we started it at 0, comma 0, it would be just the main diagonal of this graph. But anyway, though, that's the graph of this new relation, equality. And what if we did the same thing, except in this case, our sets are not the set of natural numbers, but the set of real numbers. So now we're just graphing y equals x. And I think you guys know how to do this. You probably did this when you were very early on, when you were learning how to graph. It's just a line with a slope of 1 passing through the origin. So it is the main diagonal, if you like, which has a slope of 45 degrees if you measure the angle. Anyway, that's what it looks like. And, you should notice something kind of interesting. It has, this is, if you like, a subset of the relation of points. Since the natural numbers are a subset of the real numbers, naturally the relation y equals x over the natural numbers, where now the domain and range are just the natural numbers. If we extend that domain and range to the real numbers, it kind of makes sense that you get a bigger set, namely the set of all points on this diagonal line. So anyway, and a fourth example. How about here we're going to have an inequality. So what if our graph, our relation is the set of real, again, x and y are the real numbers. So it's just a set of ordered pairs of numbers x comma y, where now y is greater than, did I say greater than? Yeah, it said strictly greater than x. And I think you guys probably learned how to do graphs like this when you were in high school as well. In this case, you just shade everything above this line. And the reason I'm drawing this I don't know how clearly you can see this, but the line that I drew in the last picture is the same line, y equals x. This relation does not contain that line because it's a strict inequality. That's why I showed this line as a dashed line. So we showed dashed if it's not included in the relation. Otherwise, it would have shown a solid line here. And you're supposed to imagine this big wedge, if you like, this big, it's actually half plane, but you're supposed to imagine extending to infinity. It extends to minus infinity. It actually extends to plus infinity the y direction and minus infinity the x direction. I think you get the idea. It's just the portion of the plane on to the upper left of the line y equals x. So that's how you would graph that relation. And finally, what if our relation is again the domain and range of the real numbers, but now our relation is given by the equation x squared plus y squared equals 1. Well, I think you guys probably learned at some point in high school that this equation is the equation of a circle. In particular, it's the equation of what we call the unit circle. It's just the circle with its center at the origin and a radius of 1. So if we graphed it, we would just get this circle. And again, I think I should point out, actually, the last two examples I did are not functions. This is not a function since every vertical line contains actually infinitely many points on this relation. And the circle is not a function either because the lines that pass through the circle, the vertical lines that pass through the circle, intersected at 2 points. And since it's more than 1 point, it's not a function. However, we could make it into a function if we restricted it to, say, the upper semicircle or the lower semicircle. But anyway, so that's how you graph relations, and hopefully this will make you more comfortable with relations. They're really just, I mean, like I said, the sets. When I was talking about when I first defined relations, I guess the reason we can graph these particular relations we've done is because each set that I'm talking about is it's a set of numbers, and in particular, a set of real numbers. And whenever whenever your domain and range are subsets of the set of real numbers, you can graph them. You can just do a Cartesian graph in the xy plane, which all these examples were. But if the sets were, say, the set of words or something, where there's lexicographic ordering of words, you wouldn't be able to graph them, at least not in any easy way. So you can't graph every relation, but you can graph relations involving numbers. Anyway, that completes my video for today on graphs of relations. Thank you for watching. Long live math, and I'll see you guys next time.